The purpose of physics is to understand the structure and behavior of nature. Now, a lot of that structure and behavior can be easily measured, directly measured and understood. Just derive some equations that explains what it is that we measure. But there's also structure and behavior that can only be indirectly measured. And the further down we go, the smaller and smaller scales that we go to, the more indirectly our measurements become, and the more we don't directly measure things. In order to learn first principles of those things, we have to infer backwards to understand them. We had to do this for chemistry even, just to understand, okay, look, it's all protons and neutrons and a nucleus, and we have electrons swirling around them. Okay, that started out as inferences. Now we have so much overwhelming evidence that we know that's the case, and that inference has been very, very successful. But there are other inferences out there that we've made that are not quite so well backed up. So for example, you have many worlds interpretations, you have theories about wormholes and white holes, perhaps even black holes. We infer that black holes exist, but we don't really know. We don't have first-hand evidence. All we have is theoretical evidence, and we have a bunch of evidence that we worked back from to say, okay, this thing called an event horizon, a singularity, all this, a black hole, would explain all these results that we have. And that's good. This is a real progress to have these inferences. But the thing about inferences is that sometimes more than one inference can fit the data. So this is really important because it applies to many of our inferences today. For example, we have quantum mechanics. Quantum mechanics has a variety of inferences from the same data. We call them the various interpretations of quantum mechanics. But remember, they're not interpretations. They're actually completely separate results. They're different inferences. They infer distinct structure and behavior. And this is what physics is about. It's not about, okay, how can we create an equation that predicts something? It's not exclusively about that. But what it is about is understanding at this point, we're trying to understand underlying behavior and structure that gives rise to everything else in nature. Okay, so this also happens in relativity. So there's this theory by Einstein called special relativity. Well, special relativity, believe it or not, is just one possible inference of the data. Another equally good inference is the Lorentz Framework. So Lorentz came up with these equations called the Lorentz transformations, and those equations are the exact same equations used by special relativity. So there's a massive difference in structure and behavior that's implied here. So on the one hand, special relativity says there's no absolute frame of reference. There's no absolute background to the universe. And on the other hand, we have the Lorentz transformations are saying, actually, there is an absolute background. It's just concealed from us. Two inferences, very different, both supported by the same data. We use special relativity now for practicality. But remember that what we really want is to get to the actual structure and behavior of nature. And let me give you the biggest tell that we don't have that yet. And that is the problem of unification. So right now, there are three separate models in physics. There's Newtonian physics, there's relativity, and there's quantum mechanics. It's a little bit of a simplification I just made, but just run with it. Three separate models. Each of those models, they employ different axioms. They don't all go back to the same axioms. They have different axioms. And so because of that, these three models don't mesh with each other. they can't mesh. They can't be merged as they currently are. And the reason why is because their foundations are different. So inferred structure and behavior functions as axioms for broader theories. Each of these three models is inferring a different kind of structure and behavior, and that's why the three models don't mix. Okay, guys, the bottom line here is that we just need to be humble about what we know, and we need to explore alternate inferences to these, to our data. If an inference is only supported by a certain cluster of data, well, it's valuable, but really we want our inferences to be supported by all of the data. And that right there is the definition of unification.